So COVID-19 really provided a unique experiment for atmosphere science to verify a potential way to improve the air quality in megacities such as Los Angeles. So first of all, I'm going to introduce by combining with the real-time sensor data and CMAC. I really appreciate the mentorship from Professor Joe Pinto and Dr. Yuan Wang. I also want to acknowledge Dr. Baron Henderson on his kind help on the CMAC result. To investigate the impact of the human behaviors on air quality, I took the data from the EPA's air quality stations as well as the more than 2,000 traffic sensors in LA Basin. The distribution of the sensors are indicated in this map. The Caltron actually also provide weight in motion system, which measured per axial weight and gross weight of the vehicles as they travel at highway speed. In this way, we can distinguish different types of the cars in LA Basin. Also, in the future, there is a potential way to use the neural networks to identify different types of the car. So first, I compared the traffic pattern from 2017 to 2019 with 2020. As you can see, starting from the March 14, the traffic flow has dropped significantly from the previous 3 years on a weekly basis. The similar trend has been observed in truck flow, and the traffic speed is the opposite. Traffic pattern actually returned back on April 14. So when we look at the daily air pollutants pattern in LA Basin, we find out that before March 14, the NO2 and the CO concentrations were generally larger than the same period in the previous 3 years. Starting from the March 15th, the NO2 and the CO concentration were generally less than the previous 3 years, and the shift in NO2 and the CO trends share the same timing due to the traffic hunting. For PM2.5, actually before the March 7th, the PM2.5 in 2020 was generally larger than the previous 3 years. Starting from the March 8th, the PM2.5 concentration in 2020 is generally less than the same period in 2017 to 2019. The ozone trend has been increased from January to April to June because of the increase of the solar radiation. Not only the anthropogenic source would have a huge impact on the air quality, but also we want to investigate the issue from the meteorological perspectives. So here are 4 panels from the air temperature, total precipitation, boundary layer height, and wind. Starting from the air temperature, when we compare current year to last 3 years, the trend seems very similar. For the total precipitation, we can see there's some precipitation during February and March, which would dilute the concentration of pollutants. So for the boundary layer height, it's still the similar trend with the previous 3 years, and the relationship between the boundary layer height and the pollutants concentration is actually reversed. When we look at the wind, we can find out the wind actually has been dominated by the sea breeze, which means the wind always blows from the ocean to the land, so we can expect a higher concentration in the riverside region versus the coastal region. To better illustrate the distribution of the data, I also use the box plots here to give a monthly pattern. So the values outside the interquartile range are shown as whiskers. The traffic flow plot is relatively tall, suggests the traffic situation varies with location and by day. The long interquartile range in traffic flow, truck flow, and traffic speed indicate that there are some traffic hotspots in specific locations and the time, which I will explain later. So for the monthly pattern, the traffic flow starts to drop on March and slowly come back again after April. So the similar trend can be observed in truck flow, although it was not as obvious as the traffic flow. For the traffic speed, it increased on March and slowly decrease after April and May. Here are box plots of pollutants comparing with the CMAQ background. There is difference between previous 3 years and 2020 during the March and June in box plots in terms of the PM2.5, NO2, and CO, which indicated there is unusual difference between those two groups due to the lockdown. The ozone plots between 2020 and 2017 to 2019 have similar size and median. And both are evenly distributed, indicating the difference between those two groups are similar. So the CMAQ background result also give us the hint that the increase of the ozone might due to the meteorological condition rather than lockdown itself. So during January and February, all figures have similar median but are slightly different in terms of the distribution, which means further investigation needs to be initiated to understand the trend at a micro level. So when compared with the box plots for the meteorology pattern, we can figure out that there are very similar trend between 2020 to previous 3 years, and again, values outside the interquartile range are shown as whiskers, so which refer the variability in the time and the spatial dimension. To offset the difference from the week versus weekend pattern, I compare the weekly pattern for all variables. As you can see that PM2.5, NO2, and the CO change gradually associating with the traffic, while all pollutants have been corresponding with a bunch of their height and the total precipitation in different levels. So I also calculate the average weekly percentage change between 2019 and 2020. The CO and the NO2 trend is generally similar, and the ozone is generally reverse trend with CO and NO2. When looking at the anthropogenic indicators, we find out that the trend of the CO and the NO2 would mostly triggered by the truck flow. So for PM2.5 is also very similar trend with the NO2 and the CO. When we're looking at the linear regression result, also show us a very strong relationship between the truck flow change and NO2 change, followed by the CO change versus truck flow change, followed by PM2.5 versus truck flow change. Because of the whiskers from the previous box plots showed us the variability from the time and the spatial dimension, so I did a 24-hour average pattern to show you the hourly variability. So basically the chart is divided by 24 slides. Each slide represents 1 hour, and the chart is consisted of 30 to 31 circles. Each circle represents a specific day. So for example, in this chart, the first circle represents the first day of January. So the last circle represents the last day of January. As we can see, before the COVID, there are very obvious double peak in the daily commute rush hour. So after the government announced the shutdown, so the double peak gradually faded away and the traffic flow decreased significantly. So it comes to the lowest traffic flow during April and slowly come back again, and you can see the double peak reappear again. So when we look at the spatial monthly average pattern for traffic flow, we can easily figure out that before the COVID, which were first two panels showed that the hotspots in the coastal region as well as the downtown, after COVID, the traffic situation gets so much relieved, especially in the coastal and the other like intersection of the highway. When come to the April, we can see, except in downtown, there are a lot of the hotspots. Other places just maintain the lowest traffic flow ever in the history. So this slide just show you the 24-hour average pattern for the truck flow. Before the COVID, there is a very obvious single peak during the day, triggered by the delivery of the consumer goods. After COVID, the truck flow got decreased, but not at the same level as the total truck flow, based on the consumption that there is still the demand from the consumer side to deliver the basic consumer goods. This is the spatial monthly average pattern for the truck flow. As you can see, before COVID, there are a lot of hotspots in the intersection region on the highway. After COVID, those hotspots slightly fade away. During the April, actually, you can expect the lowest truck flow in the history as well. This is the 24-hour average pattern for the ozone and the NO2 from the January to April. As you can see, the ozone got intensively increased from the winter to spring and summer, while the NO2 is like the opposite trend of the ozone. The ozone mostly occur during the daytime because of the UV, and it's react with the NO2 intensively during the daytime as well. So this is the trend for the May and June. The spatial pattern just very similar with the 24-hour pattern from the winter to the spring, because increase of the solar radiation. So generally in each location, the ozone get increased intensively. Also for the NO2, because of the shutdown of the traffic, it decreased on March and lowest value in the April as well. Notice there are some hotspots here. I guess it's because of the location of the warehouse, and this area could be very busy during the COVID. So we move one step further on this issue by using machine learning by cooperating with the people from Tsinghua University. So we decided to use the 3 scenarios for the traffic pattern in 2020 based on some key timings here. For example, on March 13th, President Trump declares a national emergency. On March 19th, the governor of the California announced stay-at-home order. On April 13, the governor announces a gradual plan to lift the stay-at-home order, and on May 5th, California entered stage 2. On June 12th, some zoos, bars, gyms has been allowed to reopen. So based on the data from the traffic sensor, we compare with the road shapefile to simulate the full traffic network. And based on the full traffic network, we calculate the traffic flow on that. And we use the EMFAC model from the COP to calculate emission in 3 scenarios. So this is the first scenarios pre-COVID-19. Just show you the emission strength. So this is a second scenario. As we can see, the lowest emission in this stage. So finally, when the traffic come back on the scenario 3, we can see very similar trend of the emission strength compared with the first scenarios. So this is the end of my presentation. Thank you so much for your attention. And if you are more interested in my future progress on this topic, you can follow me on the Twitter. And thank you so much.